How's it going, guys? We are going to just finish up with three-phase alternators. I'm going to post a video tomorrow on synchronous motors. But for the most part, you guys have went through everything that you're going to be going through. I'll give you some more, or take up rather the questions that I gave in the last class. Maybe give some more questions. What we had finished off with in the last class that we went through is we were starting to go through a bunch of the word problems and looking at frequency and horsepower and stuff like that. I just want to go through one of those questions quick and some of the frequency stuff, and then just do kind of a summary of everything that we've sort of been through so far, and then would like to test you on three-phase alternators next week if we can. So let's just do a quick little summary here. So I'm going to do a question. I've got let's do a 10 kVA output with a alternator that is 72% efficient and a power factor of 81%. So I want to know what the input horsepower is. The other thing I want to know is, so with this I also have a applied frequency of 75 hertz, and let's do 8 pole pairs, and I want to know what the speed is. So pause that, work through that quick, and I'll come back and then come back and do this with me. All right, so we have 10 kVA, 72% efficient, power factors 81%, 75 hertz, 8 poles. Okay. All right, so we've got our alternator. So this is going to be our input horsepower we're looking for is over here. We've got a 72% efficient alternator, and we've got 10 kVA at our output. And we've got a power factor of 81%. That's our power factor, and our efficiency is 72%. Alright, so remembering from before, in order to go through the transformer, we need to be looking at our wattage or horsepower going through. So we have to convert our 10 kVA into. Oh, that sucks. The phone died. My calculator. Need to turn that 10 kVA into a power factor. So we have 10, just give me 1 second, let me plug this back in. All right, well, that was fun. Phone turning off, honey. Okay, so we have 10 kVA, so 10,000 divided by 0.81. Actually, nope. Times 0.81. So it should be 8,100. 8,100. So when you're doing formulas again, so let's do power factor is equal to true power over apparent power, and our power factor we know is 81%, so that's 0.81, and our apparent power we have as 10 kVA, and I need to find my true power by itself, so I need to get my kVA over, so I know I have to multiply it out on both sides. So that's why I multiplied it. It's 10,000 times 0.81. So my true power becomes 8,100 watts. That's a terrible W. Another terrible one. Or 8.1 kilowatts. Okay, so that's what our output power is over here. So we've got an output power of 81 kilowatts. And now we need to find what our input power is based off of 72% efficiency. So percent efficiency is equal to power out over power in. We have a percent efficiency of 0.72. We have our output power of 8.1 kilowatts, and we have an unknown input power. And remember what we were saying before, rather than trying to rearrange the entire thing, easy trick is you just flip those. So 0.72. Our power in. So 8.1 divided by 0.72. And it should always be a larger number, remember? Our input is always larger, and we have losses through our alternators, so then the value is going to be smaller on the other side. And that gives us a value of 11.25 kilowatts. So that's what our input power is. So we have our input power, then our losses, and then because of either inductive or capacitive reactive loads, we end up seeing a larger number for our power factor at the end. Okay, so now let's just run on to the next part, and the next part of this is going to be our overall speed. So frequency is equal to poles times speed divided by 120. Our frequency is 75 hertz. Our poles are 8. We don't know our speed divided by 120. So we need to get N by itself, so multiply 120 on each side. So we have 75 times 120 is 9,000. And we have now 8N over here. We want to get N by itself, so we divide 8 out on both sides. So N is equal to 9,000 divided by 8. So our speed is 1,125 RPM at the end of the day. Hopefully that wasn't too bad for you. Okay? Once you get into the routine of doing it, they're fairly easy to do. It's just getting the practice in. Alright. I am going to just run through three-phase alternators quick. Just quick little blurb on them as we go through. So if you remember, with a three-phase alternator, we have a prime mover. That prime mover could be a motor, could be a turbine, could be a fan, could be some form of hamster wheel, whatever it is. We just need something to spin the shaft of that alternator. So whatever it is spins that shaft. If we don't have DC excitation, that shaft that comes through the center of that alternator, all it's going to do is spin. It's just metal and copper windings spinning. There might be a little bit, but it's negligible, but there's no residual magnetism inside that alternator on the shaft of that motor. So because there's no residual magnetism, we have to create a magnet in the center of that alternator. So the shaft, as you remember, whether it is via slip rings and voltage getting on, or whether it is and I encourage you to go back and look at a couple of the other videos before the test, and then also read through alternators and Dalmars. There ends up being a little three-phase generator where we have magnets on either side of the shaft, and as the coils spin around, it induces a three-phase voltage onto the shaft of that alternator. It then goes through a three-phase rectifier. After it goes through the three-phase rectifier, now we have pulsating DC. It then goes through a capacitor to filter, and then we end up having a solid DC voltage that then goes out to the field. We can't have pulsating voltage on the shaft because the magnet would be there, then disappear, be there and disappear. So we always have to make sure that it is pure DC. So that's why you could either do DC on slip rings out, but those slip rings and the brushes end up wearing down over time. So that's why I use a little generator on the shaft of that alternator. But as soon as I turn on that DC excitation, I end up getting voltage. Voltage ends up being established. And once that voltage is going through those windings or through those poles, and there's salient poles, and salient poles are poles that extrude out from the shaft of the alternator. Once I end up having that voltage going through and current flowing through, I end up producing a magnetic field that is now all around the shaft of that alternator. Actually, I may not go into, yeah, we'll see. Sorry, I'm just thinking about things. So that ends up going and creating a magnetic field that is now inside the center of that alternator. So if there's no prime mover, that magnet is just there sitting. So I need rotation from something else. And as it rotates, that magnetic field rotates, it starts cutting the windings inside the stator, those three-phase windings spaced apart, and as the magnet cuts through your phase 1, phase 2, phase 3, it ends up creating that pulsating DC voltage that pulsating three-phase AC voltage that we need. For the startup, there's not really too much other than that you need to be concerned with. The only other thing is the field discharge resistor, or the diode put in reverse, that when I go to turn off that magnetic field, that's created on the shaft of that rotor. There can be a collapsing magnetic field that can end up ruining the electronic parts circuitry on that board. So that's why the resistor is there to dissipate that voltage. Other things to be concerned with, other than the formulas for when we end up doing the test, was going through the paralleling of alternators. And with the paralleling of alternators, as you guys remember, there are 4 things that were required. We needed to have the same voltage between alternators. We needed to have the same frequency. We needed to have the same phase rotation, and that did not mean that the alternators had to be spinning the same way, because we can change a line 1, line 2, and end up changing the output frequency, or the output rotation. So it's just that the frequency goes ABC, ABC, ABC between the two of them. So rotation wasn't necessarily, and with the frequency, that speed wasn't necessary. Speed is not a requirement, but frequency is, because if I had 2 different alternators that were running at different speeds, but then had the proper amount of poles to give me the same frequency output, then that's of what's required than just speed. So voltage, frequency, same phase rotation, and then same in-phase opposition. And in-phase opposition was that they're meeting their peaks at the exact same time. You don't want one to be high and one to be low, because then you have a huge potential difference when you go to close that synchronizing switch. So you get those 4 things in. Once all 4 of those are done, you've achieved all those, you can then close that synchronizing switch. And remember, before we closed it, that 3 light method, those light bulbs were around that breaker. Well, once you end up closing that synchronizing switch, it ends up completing the path, or shorting out those lights, so that you've got a complete path between the 2 of them, and now they are synchronized. However, the only last part was that we needed to switch the load from the one alternator to the other alternator, and the only way to do that was to transfer the load slowly from one to the other. In order to do that, you needed to decrease the power of the one that had the load and increase the power of the one that was going to be taking on the load. In order to do that, you would reduce the speed of the one that had the load, therefore reducing the power output of the alternator, and increase the speed of the one taking the load, therefore increasing its power output. So that's the way to transfer it, and once they're completely transferred, then you could turn off that first alternator. But yeah, I would encourage you to go back and watch the videos that we went through, and maybe look through some of those charts that we I went through and looked at. And in lab class Friday, if you have any questions, feel free to go through with me then. Last thing I want to go through, or last thing I want to do right now, is that I want to do a quick little talk on 3-phase motors, synchronous motors. I won't get into a huge amount with it right now. And that is with a 3-phase motor The shaft is all the same. You've seen in lab that a three-phase motor and three-phase alternator, there wasn't a whole lot. Other than a motor starter, there wasn't much difference between the two. So the shaft construction of a three-phase synchronous motor is the exact same way as it is on a alternator. So we have our DC excitation added the same because we still need DC excitation. So I'll just draw that quickly out. So I've got my three-phase coil between two magnets, right? So that could just be a little battery there. So then I've got windings going through that bad boy. So that I've got a three-phase, basically alternator on the shaft. And this is a good review for your other test. And that then comes out to a bridge rectifier. And with our bridge rectifier, we ended up having our three-phase voltage and we had our 6 diodes. So that was our three-phase bridge rectifier, and the three-phase bridge rectifier would then come out to a filter, to filter that, and then it would come out to our field. So that's the field at the shaft, so that's our positive, negative, and that's what produces the voltage, the DC voltage on our salient pole. So I've got that, all of that is on the shaft, and then it comes out to our big magnet, the north and the south, and then that is spinning inside between on the in the now motor. Construction of the three-phase motor, synchronous motor, is the same as with the three-phase alternator. So I end up having my alternator, and I've got poles with coils on them. They're actually in pairs and drawn by themselves, but I've got phase A, B, and C inside that motor shaft, or inside inside the motor body. But when we go through to turn on a three-phase synchronous motor, there are a few things that we had to keep in mind. So three-phase motors. With a three-phase motor, when we go to start it up, how do we establish a rotating magnetic field? So rather than spinning a magnet in coils, now we energize coils, and those coils then end up creating rotation on the shaft of that motor. So before we start it up, we disconnect. Actually, I'll draw that as a battery, and I'm going to open up the switch. This is their switch to turn on our DC excitation. So we've got our shaft, and we've got a phase A, B, and C. And how do we supply a three-phase voltage to a three-phase motor? Well, the simple answer is just supply power to it. So, you know, either turn on your motor starter or turn on your switch or whatever you have to supply it. As soon as I supply voltage to a three-phase motor, I end up getting a rotating magnetic field. And if you remember, I've got a three-phase sine wave, looks like that. So this would be my A, B, C. So in the first fraction of a second, that one sees a voltage. So once I see a voltage and current is flowing, then a magnetic field forms. So I get magnetic field formed this way. Then I get current now on B showing up here. So my magnetic field is now here as that one's collapsing. Then as this one's collapsing, I get my phase 3 being created. So my magnetic field goes from being this way to being this way to being this way, that way, that way, that way, that way, that way, that way, and I end up getting a rotating magnetic field inside the center of the motor. If I were to close this on startup and created a magnet in the center, if that magnet was there and was strong before I turned on my three-phase rotating magnetic field, let's say A energized, the north would try to be attracted to that magnetic field. Before it's even got a chance to start moving, my magnetic field would be here, then it'd be here, then it'd be here. Remember, that's rotating in the lab, a rotating magnetic field is turning at 1800 RPM. So before that shaft could even get up and going, the magnetic field would now be here and it'd be trying to pull that shaft back the other way. And when it went to pull back the other way, then my magnet's here. So I'd end up getting a locked rotor in the center of that machine. And I would have a huge amount of current going through that, which would damage a lot of stuff. So I always want to make sure on startup that my DC excitation is de-energized, so I don't have a magnet. So on startup, what I want to do is I just want to leave that DC excitation off. I want to turn power on to that machine so that I can get a rotating magnetic field. And once I get a rotating magnetic field, there's a very interesting thing in these, and we didn't talk about them when it was with respect to an alternator, but there's an amortisseur winding. I believe it's, if you can see up that high, I'll get rid of that so you can, I believe it's, I think it's 2 M's, or maybe 1 M. I think 1 M, 2 S's. I think it's like that, amortisseur winding. And that amortisseur winding is around those salient poles. So the shaft of my motor would come around, this would be my shaft, and I'd have all of my three-phase windings all inside here, creating poles all the way around the outside of that rotor, and that amortisseur winding would be around it. That amortisseur winding is either copper, aluminum, or steel bars, thin bars that go around all of the coils, and it's got solid rings on both sides, and those solid rings complete a path for current to flow. So if I end up having a magnetic field traveling around inside this motor, those magnetic lines of flux are going to end up wrapping around and cutting past the bars of this amortisseur winding. And if I have a completed circuit, so I have a path for current to flow, as those lines of flux cut those bars, I'm going to end up inducing a voltage and current into those bars, which in turn is going to produce a magnet. So I'm going to produce magnets or a magnetic field on that amortisseur winding, and that magnetic field is going to be attracted to the magnetic field of the rotating magnetic field, which is obviously going to spin the shaft of that motor. So that's why when we go to start up the motors in the lab, we go to hit start. And remember, they kick up the speed, but they don't quite get up to synchronous speed. And the reason for that is I always need to have relative motion between my amortisseur winding and my rotating magnetic field. So this one might get up to 1,798 RPMs, while this one's at 1,800. And the reason why I need relative motion is if there's no relative motion, so if these are both the same speed, there's no lines of flux being cut. If there's no lines of flux being cut, then I don't induce a voltage, I don't induce current, and I don't create a magnetic field on the shaft. So this always has to be slightly slower. So even if it was going to be able to get close or right up to that speed, it would end up falling back a little bit because it would lose its magnetism. So even if it got there on startup and end up going the same speed, it would end up falling back a little bit because I need to have some lines of flux being cut to induce that voltage, current, and magnetic field. With that being said, I can't load this down or can't run it for a long period of time just with the amortisseur winding creating that motion of that motor. Because what happens is the amortisseur winding is made of small copper, aluminum, or steel bars, and if I put under load or leave it for a longer time, that current is going to keep building up and building up, or not so much building up, but it's going to start heating up that amortisseur winding more and more and more, and what will end up happening is that amortisseur winding will burn out and then the motor will be screwed. So the amortisseur winding is only to get the motor up to speed. Once the motor is up to almost synchronous speed, we then close our DC excitation switch, and then that ends up producing our three-phase voltage that gets rectified, comes out and gives me a north and a south. And that's when we get that bump where it goes boom once we go to flip it on, and that's the two fields getting locked together. So our rotating magnetic field around the outside in the armature and the rotating magnetic field of the shaft now both have strong magnets, and because there's not a huge amount of relative motion between the two, that pole now can become in sync with the rotating magnetic field, so now they'll be synchronized together. And I know this doesn't really truly show it, but however many poles are in the armature, the same number of poles are going to be on the shaft. So I just did one magnet, but if I have, let's say, 12 poles around the outside of that motor, my shaft of my rotor is also going to have 12 poles on it. They're matched so that there's a pole in the rotating magnetic field for every pole on the rotating rotor. Okay, so they are the same. So just make a little note that the same number of poles on the shaft of the rotor as there are in the stator. So now our motor is up and running and will continue to be synchronized. The nice thing about these motors is that they are considered to be a constant speed motor. So that's a little note, write down constant speed motor, that'll be on the test. And then another thing is any motor that's runs at a speed of more than 500 RPMs is considered a high-speed motor. So that's another one. Those are two answers, I believe, directly for the test, so you can write those down. But yeah, so I just had a brain fart on what it said. So I said high-speed motor, and then I can't remember the other thing I just mentioned. But either way, now the two are linked together and they're running. One important thing is, that it's a constant speed motor. It doesn't matter what happens to it. So if I load it down, typically when you load a motor down, what happens to it? Well, that motor begins to get slower and slower and slower. And then more lines of flux ends up being cut, so that ends up in improving the torque and allows to push that, drive that load. But in this case, and I'll talk about the torque stuff in the next video, but in this case, they are always linked together. They will always run at the same speed until they won't. What basically happens is, rather than it getting smaller, there ends up being a little torque angle in there, so it begins to lag slightly behind. So I'll give you an example. So if we, and I'm not sure if I've mentioned in class, but let's say I was driving down the road and I had a truck with an elastic, or a truck holding a trailer with an elastic joining the two. If I end up loading down that trailer is going to start stretching that elastic, right? As I load it down and load it down and load it down, it's going to stretch more and more and more. But just because it's stretched doesn't mean it's not moving at the same speed. So even when I've almost fully loaded that motor down, I'm going to have a huge stretch of that elastic band, right? But they're still moving in unison. They're still moving at the same speed. So even if I load this guy down, that rotor shaft is still going to be moving the same speed as the synchronous magnetic field. It just has basically strain. So what happens is that rotor is not completely lined up with the pole of the stator. So, and I know these actually are stationary in the magnetic field spinning, but if that's the pole of the motor and this is unloaded, so this would be stator, rotor, and they're lined up. As I go to load down that motor, what ends up happening is it ends up getting stretched behind slightly. So now my rotor is slightly behind, but it's still moving at the exact same speed. And it will remain at that speed until it gets pulled out of step. And the problem is when you finally get to that point where you've overloaded that motor, it'll pull it out of synchronism. And just like that elastic band, once you put too much weight, that elastic band's gonna break. And what's gonna happen to the trailer? That trailer's gonna nosedive, it's gonna fall out. Same thing with this motor. When it gets completely overloaded, it breaks that connection and the motor is going to end up stalling out, which is going to cause a huge amount of damage to that motor. Okay. As for synchronous motors, I'm not going to add anything further to that. Hopefully that was a good start, and you can watch the video tomorrow, and you will see me Friday in lab class. Okay, have a good one. Bye.